In January of 1986, a spacecraft the size of a small car swept past a pale blue-green sphere at the edge of what we then considered the known solar system. It stayed close enough to matter for only a few hours. It sent back its pictures, its numbers, its brief impression of a planet spinning nearly on its side in the dark. And then it kept going, out toward the stars, never to look back. For the next 40 years, that was Uranus, a single flyby, a single mood, captured on a single day, treated as if it were the planet's permanent personality. Textbooks called it bland, featureless, the dullest of the giant planets, a plain, pale marble with nothing to say for itself. Scientists moved on to more exciting worlds. Funding moved on. Uranus became the planet you skipped past on the way to somewhere more interesting. But something strange has been happening in observatories over the last several years. Astronomers pointing newer, sharper instruments at that same pale sphere have started finding things that should not exist on a boring planet. Storms larger than entire countries, a magnetic field that behaves like nothing else orbiting the sun. Hints that the interior of the planet may not be made of what we assumed at all. Even the very glimpse Voyager gave us, it turns out, may have caught the planet on an unusually quiet day, not a typical one. We are living through the slow, quiet unraveling of nearly everything we thought we understood about the seventh planet from the Sun. Not through a dramatic new mission, not yet, but through rereading old data with new eyes, and through telescopes patient enough to watch a distant world breathe. Tonight, we drift out past Saturn, past the orbit of the ice giants, to a planet tipped over on its side, spinning through darkness 19 times farther from the Sun than Earth. A planet we have visited exactly once. A planet that may be rewriting the rules of what a world can be, one faint signal at a time. This is Uranus, and this is the story of how little we actually know. There is something quietly unsettling about building a scientific consensus on a single encounter. Yet that is the position planetary science found itself in for 4 decades, and it began on a cold winter day in 1986. Voyager 2 had already done astonishing work. It had flown past Jupiter and revealed volcanoes erupting on a moon called Io. It had swept past Saturn and returned images of rings so intricate they looked hand-carved. By the time it approached Uranus, the spacecraft was 7 years and nearly 3 billion kilometers into its journey, roughly the distance of 18,000 round trips between New York and Los Angeles. Its instruments were aging. Its power was dwindling, generated by the slow decay of plutonium rather than sunlight, because at that distance, sunlight is a rumor rather than a resource. Uranus receives only about 1/400th of the sunlight that reaches Earth. If you stood on its cloud tops at noon, the sun would look like nothing more than an unusually bright star. Voyager's closest approach came on January 24th, 1986. The spacecraft passed within about 81,000 kilometers of the planet's cloud tops, a distance that sounds vast until you remember that this was the only time humanity would ever get this close. For a period of only a few hours, every instrument aboard turned its full attention toward Uranus, and then the encounter was over. Voyager continued outward toward Neptune and eventually toward the edge of the solar system itself, and it never looked back. What it saw in that brief window was a planet almost defiantly calm. The cameras returned images of a smooth, pale blue-green ball, nearly featureless from pole to pole. No swirling storms like Jupiter's great red spot, no visible banding like Saturn's, just a soft, uniform haze, tinted that color by methane gas in the upper atmosphere, absorbing red light and reflecting blue back into space. Scientists at the time were, by most accounts, disappointed. Here was a giant planet that seemed to have nothing to say for itself. One researcher famously compared it to a cue ball. The comparison stuck, and Uranus quietly became known, in scientific circles and popular science alike, as the boring planet. That impression calcified. For the next 30 or so years, mission planners, scientists, and funding committees treated Uranus as a low-priority destination, precisely because Voyager had shown so little of interest happening at its surface. Why send an expensive, decade-long mission to a planet that appeared to be doing nothing? The single flyby became, in a very real sense, the ceiling on Uranus science. Every model of its atmosphere, every assumption about its activity level, traced back to those few hours of data. Here is where the story takes its first genuinely strange turn. In recent years, researchers going back through the archived instrument readings from that flyby noticed something that had been hiding in plain sight. In the days before Voyager arrived, the solar wind, the constant stream of charged particles flowing outward from the sun, happened to surge unusually strongly. That surge compressed Uranus's magnetic environment dramatically, squeezing it down to a fraction of its normal size and altering the behavior of the charged particles trapped around the planet. In other words, Voyager did not simply photograph Uranus on an average day. It arrived during a rare, compressed, almost anomalous solar weather event, one that researchers now estimate occurs only a small percentage of the time. It is a little like sending a single photographer to document a bustling, ever-changing city, only to have them arrive during an unusual lull, a quiet Sunday morning mistaken for the city's constant rhythm. Everything humanity believed about Uranus's magnetosphere, based on years of secondary analysis, was built on an atypical sample of one. This single realization forces a humbling recalibration. The bland, quiet planet of 1986 may never have been particularly bland or quiet at all. It may simply have been caught for a few unlucky hours in an unusual state, and an entire generation of science treated that snapshot as the rule rather than the exception. It raises an uncomfortable question that will echo through the rest of this documentary. If a single, brief flyby, compressed by unlucky timing, shaped 4 decades of assumptions about a planet's magnetic environment, what else might it have gotten wrong? What else, hiding beneath a calm blue-green surface, was never really calm at all? Every school child who studies the solar system eventually learns to sort the planets into families. Rocky worlds close to the sun, gas giants in the middle distance, and out past Saturn, the so-called ice giants, Uranus and Neptune, worlds supposedly built around a deep mantle of exotic ices, water, ammonia, and methane, compressed and heated until they behave more like a thick, slushy ocean than anything you would recognize as ice back on Earth. That word, ice, is where the first deep uncertainty begins. In planetary science, ice does not mean the frozen cubes in your freezer. It refers to any of several compounds, water, ammonia, methane, that would be gaseous or liquid on Earth's surface, but which planetary scientists group together because of how they behave chemically in the outer solar system. Deep inside Uranus, these so-called ices are neither frozen nor liquid in any familiar sense. Under crushing pressure and searing internal heat, they exist as a dense, electrically conductive fluid, something closer to an exotic, superheated slush than to anything resembling a glacier. It is a strange linguistic inheritance, this idea of an ice giant whose ice might be hotter than the surface of Venus. For decades, the standard model of Uranus's interior described three broad layers. At the center, a relatively small, rocky core. Surrounding that, an enormous mantle of this hot, dense ice fluid, making up the bulk of the planet's mass. And atop it all, a comparatively thin atmosphere of hydrogen and helium gas, the part we actually see through telescopes. This layered model was elegant. It fit reasonably well with estimates of Uranus's mass, size, and gravitational field, calculated from the same limited Voyager data and subsequent Earth-based observations that shaped so much of our understanding. But newer interior modeling, run using the increased computing power and improved equations of state that scientists now have available, tells a more uncertain story. Some models suggest Uranus's interior may not be a clean, tidy, layered ice mantle at all. Instead, it may be considerably rockier than the traditional picture allows, with rocky material more thoroughly mixed throughout the interior rather than concentrated in a small central core. Under this view, Uranus might be less a smooth layered ice giant and more a partially blended world, rock and ice and gas folded together in ways that resist simple categorization. Why can we not simply settle this question? The honest answer is that we are trying to diagnose the internal structure of a world 25,000 kilometers across using only the faintest external clues gathered from a single brief spacecraft visit and a scattering of remote observations since. Two of the biggest limitations stand out. First, gravity data. When a spacecraft passes near a planet, tiny variations in the planet's gravitational pull, caused by how mass is distributed inside it, subtly tug on the spacecraft's trajectory. Careful measurement of those tugs lets scientists infer interior structure. But Voyager's single flyby yielded only a limited, imprecise gravity dataset, nowhere near detailed enough to settle the debate. We are effectively trying to reconstruct the layout of a house from a single blurry photograph taken through a curtain. Second, there is the deep question of convection. Does heat move through Uranus's interior the way it moves through a pot of boiling water, in great turning currents that would tend to mix the interior into a more uniform blend? Or does the interior sit in stable, layered strata, like oil resting undisturbed atop vinegar, each layer never quite mixing with its neighbors? The answer matters enormously because a convective interior would tend to blend rock and ice together over billions of years, while a stable, layered interior would preserve sharper boundaries between them. Different research teams, working from the same limited data set, currently favor different answers. This is not a case of scientists disagreeing over a minor technical footnote. This is a live, open, genuinely unresolved question about the basic composition of a major planet in our own solar system. Is Uranus fundamentally an ice giant, true to its name? Or is it something closer to a rock giant, wearing a thin blue-green atmosphere as a kind of disguise? At present, honestly, nobody knows for certain. The most responsible answer any planetary scientist can give you is that both models remain plausible, and that only new, far more detailed gravity and magnetic field measurements, the kind only a dedicated orbiter could gather, will be able to resolve it. Consider, too, why this question matters beyond simple curiosity about labels. The proportion of rock to ice inside Uranus shapes almost everything else we might want to understand about the planet. It influences how the interior generates or fails to generate heat, a mystery we will turn to directly in the next chapter. It shapes how the planet's magnetic field is produced, since a rockier, more electrically conductive interior behaves very differently from a deep fluid ice mantle when it comes to generating and channeling magnetic currents. It even bears on how Uranus formed in the first place, whether it accumulated primarily from icy planetesimals far out in the young solar system's cold outer reaches, or whether it captured a larger share of rocky material earlier in its formation than current models assume. A single unanswered question about interior composition ripples outward into nearly every other open mystery this planet holds. There is something almost poetic about a planet whose very name may be built on an assumption we cannot yet confirm. Ice giant was never meant to be a permanent label. It was a working hypothesis, born from one glimpse, waiting patiently for 40 years now, to be tested properly. Every giant planet in our solar system generates its own internal heat, radiating more energy out into space than it receives from the sun. Jupiter does it. Saturn does it, dramatically so. Even distant Neptune, sitting roughly 1.5 times farther from the sun than Uranus, glows with noticeably more internal warmth than its inner neighbor. This is one of the quiet, elegant regularities of planetary science, a kind of thermal signature that giant planets are expected to share, left over from the violent heat of their formation, slowly leaking outward across billions of years. Uranus, for decades, appeared to break this rule entirely. Early measurements, again largely rooted in that single Voyager flyby and subsequent Earth-based observations, suggested that Uranus radiated barely any more energy than it received from the sun, essentially in thermal balance, giving almost nothing away. This made Uranus something of a scientific outlier, an anomaly among giants, a world that seemed to have simply run cold sometime in its deep past. It also produced one of the more delightfully counterintuitive facts in planetary science. Despite being significantly closer to the sun than Neptune, Uranus holds the record for the coldest atmospheric temperature ever directly measured on any planet in our solar system, plunging to roughly minus 224 degrees Celsius in its upper atmosphere. Neptune, farther from the sun and therefore receiving even less sunlight, should by simple logic be the colder of the two. Instead, because Neptune keeps generating substantial internal heat while Uranus apparently does not, Neptune actually runs warmer overall. Distance from the sun, it turns out, is not the only thing that determines a planet's temperature. What is happening deep inside matters just as much as what is shining down from outside. For years, this heat deficit was treated as simply another data point, filed away without a clear explanation. But more recent energy balance studies, drawing on decades of accumulated infrared observations from ground-based telescopes and orbiting instruments, have started to complicate that picture. When researchers carefully reanalyze how much energy Uranus actually absorbs from sunlight and compare it to how much the planet emits back into space, the numbers now suggest that Uranus does, in fact, emit a small amount of excess internal heat. not much, nothing like Jupiter's dramatic internal furnace, but a faint, persistent trickle, more than the old picture of total thermal silence would allow. Why would a giant planet's internal heat, something that should simply be a byproduct of gravity, slowly compressing material since formation, run at only a whisper compared to its siblings? Several hypotheses currently compete for the honest, if unglamorous, title of leading candidate. One possibility ties back to the layered interior question from the previous chapter. If Uranus's interior truly does sit in stable, distinct layers rather than churning convective currents, that layering could act almost like insulation, trapping primordial heat, the original warmth left over from the planet's violent formation, deep within the interior, rather than allowing it to rise efficiently to the surface and radiate away. Under this view, Uranus might not lack internal heat so much as it hides it unusually well, sealed beneath layers that resist the normal outward flow. A second hypothesis reaches back to an event we will explore in detail in the next chapter, a colossal ancient collision that may have knocked Uranus onto its side. Such a violent impact, some researchers suggest, could have profoundly disrupted the planet's original internal structure, potentially altering how heat is generated and distributed to this day, tens of millions or even billions of years later. A planetary scale collision does not simply reorient a world's spin axis and then leave everything else untouched. It could, plausibly, have scrambled the deep thermal architecture of the entire planet. Neither explanation has been confirmed. Both remain genuinely open lines of research actively debated among planetary scientists who study heat flow and interior structure. What has changed, meaningfully, is the shift away from the old simple story of a thermally dead planet toward a more nuanced picture of a world that may be quietly radiating heat it has spent eons trying to keep hidden. There is something almost fittingly Uranian about this, a planet with a reputation for being cold and inert, turning out on closer and more patient inspection to be faintly, stubbornly warm underneath. Sometimes the loudest conclusions get overturned not by dramatic new evidence, but by decades of quiet, careful recalculation. Every other planet in the solar system spins in a manner that, broadly speaking, respects the plane in which it orbits the Sun. Earth tilts a modest 23.5 degrees, enough to give us seasons, not enough to fundamentally upend how sunlight reaches us throughout the year. Jupiter barely tilts at all. Even Saturn, with its dramatic rings, leans a comparatively gentle 27 degrees. Uranus does something no other planet does. It tips over almost completely, its axis tilted roughly 98 degrees relative to its orbital plane. In practical terms, this means Uranus does not so much spin like a top as it rolls like a ball along its orbital path, its poles taking turns pointing almost directly at the Sun. Try to hold that image in your mind for a moment. Imagine standing at Uranus's North Pole during its brief midsummer. The Sun would not rise and set the way it does on Earth. Instead, it would remain fixed nearly overhead, day after day, for years at a stretch, while the rest of the planet experienced something closer to a twilight of unimaginable length. Because Uranus takes 84 Earth years to complete a single orbit around the Sun, each of its poles experiences roughly 21 years of continuous sunlight, followed by 21 years of unbroken darkness. A single Uranian season lasts longer than most human childhoods and early adulthoods combined. A person born at the start of a Uranian winter at one pole would, by the time sunlight finally returned, be well into what we would consider middle age. What could possibly knock an entire planet, one of the largest bodies in the solar system, onto its side so dramatically? The leading explanation, supported by a growing body of computer modeling, points to violence in the deep past. Sometime in the earliest, chaotic period of the solar system's formation, when planetary-sized bodies were still colliding, merging, and being flung across a young and disorderly solar system, something enormous appears to have struck Uranus. Current models suggest the impactor may have been roughly the size of Earth, or possibly even larger, striking Uranus at a glancing angle rather than head-on. Picture that collision for a moment, the way you might picture a scene from a nature documentary about deep time. Two planetary bodies, each larger than anything humans have ever directly encountered, approaching each other across the young solar system at tens of thousands of kilometers per hour. The impact itself would have unfolded over a span of hours, an event of such scale that it briefly outputs more energy than the sun itself produces during that same window. Uranus's outer layers, its atmosphere, and upper mantle would have been violently disturbed, material flung outward, some of it falling back, some of it potentially forming the seeds of the moon system we see today. And the planet's fundamental spin, the orientation locked in from its original formation, would have been wrenched sideways, tipped over by the sheer transferred momentum of the strike. This single ancient event, if the model holds, may explain far more than just the planet's odd tilt. Consider the moons. Uranus's major satellites orbit not around the planet's original equatorial plane, but around its current, tipped-over axis, circling almost like the hands of a clock lying flat on a table rather than standing upright. This strongly suggests the moons, or at least their current orbital arrangement, formed or were significantly reshaped after the tilting impact, consistent with debris from the collision settling into orbit around the newly reoriented planet. Consider also the strange interior we discussed 2 chapters ago, a collision violent enough to knock an entire ice giant onto its side would almost certainly have disrupted whatever clean, layered internal structure existed beforehand, potentially explaining why Uranus's interior remains such a stubbornly ambiguous puzzle, resistant to the tidy models that work reasonably well for other giant planets. And consider the heat paradox from the previous chapter. Some researchers propose that this same ancient impact may have disrupted the planet's original heat, generating and heat-transporting mechanisms, contributing to the faint, unusual thermal signature we still detect today, echoes of violence billions of years in the past, still faintly audible in the planet's present-day energy budget. It is worth being honest about the limits of this picture. The giant impact hypothesis remains a leading theory, not a settled fact. Alternative explanations involving more gradual gravitational interactions with a massive early moon or complex resonances with the other giant planets during the solar system's turbulent youth have also been proposed, and the debate among specialists continues. But the giant impact scenario currently commands the widest support precisely because it offers a single, elegant explanation that ties together so many otherwise disconnected oddities: the tilt, the moon orbits, the ambiguous interior, and perhaps even the faint internal warmth. There is a further detail worth sitting with because it changes how we should picture the collision itself. A perfectly head-on impact would likely have produced a very different outcome, perhaps shattering the young planet outright or driving its spin in a more extreme, chaotic direction entirely. The glancing nature of the impact, currently favored by modeling, a grazing strike rather than a direct hit, is precisely what allows the planet to have survived largely intact while still having its rotation dramatically reoriented. It is the difference between a car surviving a sideswipe on the highway and a car meeting a wall head-on. Uranus, under this picture, absorbed a blow that could easily have ended its existence as a coherent planet, and instead emerged merely tipped over, scarred but whole, carrying the consequences of that near miss for billions of years afterward. Uranus, under this view, is not simply a planet that happens to be strange. It is a planet still visibly wearing the scars of the most violent event in its entire history. A scar so severe it rewrote the planet's very sense of up and down, and one so old it happened while the sun itself was still a relatively young star. Return for a moment to that image from 1986, the cue ball, the bland, featureless sphere that convinced a generation of scientists that Uranus had simply nothing interesting happening at its visible surface. For decades, that image held. Ground-based telescopes of the era simply were not sensitive enough to challenge it, and Uranus receded from scientific attention, a world seemingly confirmed as quiet. Then, starting in the 1990s and accelerating through the 2000s and into the present decade, something changed, not on Uranus, but here on Earth. The Hubble Space Telescope, along with large ground-based observatories equipped with adaptive optics technology capable of correcting for the blurring effects of our own atmosphere, began returning images of Uranus with a level of clarity Voyager's cameras could never have achieved from such a distance. And what these new eyes revealed bore almost no resemblance to the placid cue ball of scientific memory. Bright clouds began appearing in image after image, distinct features rotating with the planet, sometimes brightening dramatically over the course of just days. Seasonal changes became visible as well, a slow brightening and darkening tied to Uranus's extraordinary 84-year orbit and its extreme axial tilt with a distinct polar hood, a bright collar of haze, forming and dissipating around whichever pole currently faced the sun most directly. The most striking demonstration came in 2014, when astronomers using large ground-based telescopes documented an extraordinary outburst of storm activity on Uranus, a series of enormous bright cloud features that developed and evolved over a period of weeks, unlike anything the supposedly quiet planet had shown in decades of prior observation. These were not minor atmospheric ripples. Some of the individual storm features tracked during this period were large enough that, had they occurred on Earth, they would have spanned distances comparable to entire countries. For a planet with a reputation for absolute atmospheric calm, this was nothing short of remarkable, and it forced a serious reconsideration of how dynamic the Uranian atmosphere might actually be. Since then, a patient, multi-decade monitoring campaign using the Hubble Space Telescope has built up something Voyager's single flyby could never provide, a genuine long-term record of how Uranus changes over time. Rather than one snapshot, scientists now have roughly 2 decades of repeated observations, allowing them to track actual seasonal evolution as Uranus slowly proceeds along its 84-year orbit. This long baseline has revealed genuine atmospheric seasons, changes in cloud brightness and distribution that track with how directly sunlight strikes different latitudes as the planet's extreme tilt slowly shifts which hemisphere faces the sun. What causes these storms precisely remains an active area of research, but the working picture involves the slow, complex interplay of sunlight, methane condensation, and deep atmospheric convection. As different regions of Uranus's atmosphere receive varying amounts of sunlight across its extraordinarily long seasons, temperature differences build between layers, eventually triggering convective upwelling, warmer material rising, cooling, and condensing methane ice crystals into bright, reflective clouds. Not unlike how convective thunderstorms build on Earth, just operating on a scale and timescale almost impossible to intuitively grasp. A single Uranian storm system may develop and evolve over a period that would qualify, on Earth, as an entire extended weather season. There is a genuine irony worth sitting with here. The planet declared boring based on a few hours of direct observation has, on renewed and patient inspection, revealed itself to be host to some of the more dramatic individual storm outbursts documented on any planet in the solar system. It simply took decades of accumulated patience, rather than a single hurried flyby, to notice. This pattern, a planet appearing calm only because we did not look long enough or carefully enough, will recur throughout the rest of this documentary, and it deserves to sit with you for a moment. How much of what we consider settled, boring, or fully understood about the universe is simply the result of not yet having watched for long enough? If Uranus's storms represent one of its more visually striking surprises, its magnetic field represents perhaps its strangest and most genuinely alien behavior, a feature unlike anything else documented anywhere in the solar system. Every planet with a strong internal magnetic field, Earth included, tends to have that field behave in a broadly predictable way. Picture Earth's magnetic field as a simple bar magnet, roughly aligned with the planet's rotation axis, its magnetic poles sitting reasonably close to the geographic north and south poles, and its overall structure centered close to the planet's actual physical center. It is not a perfect alignment. Earth's magnetic field wobbles and drifts over time, but it is close enough to that simple picture that compasses have reliably guided travelers for centuries. Uranus abandons this tidy picture almost entirely. Its magnetic field is offset dramatically from the planet's physical center, displaced by a significant fraction of the planet's own radius, as if the magnet generating the field were not centered inside the planet at all, but shoved noticeably off to one side. On top of that offset, the magnetic field is tilted an extraordinary 59 degrees away from Uranus's rotation axis. For comparison, Earth's magnetic field tilts only about 10 degrees from its rotation axis. Uranus's field is tilted more than 5 times as steeply. Now combine that already unusual magnetic geometry with the planet's extreme 98-degree axial tilt, the sideways spin we explored earlier, and something genuinely unique in the solar system emerges as Uranus rotates on its 17-hour day, and as the whole planet simultaneously tumbles along its 84-year orbit with its poles alternately facing the sun. The magnetic field, already wildly misaligned from the rotation axis, sweeps and wobbles through space in a manner no other planet's magnetic field does. The most visually striking consequence of this geometry involves what planetary physicists call the magnetotail, the elongated, windsock-like extension of a planet's magnetic field that trails away on the side facing away from the sun, shaped by the constant outward pressure of the solar wind. On most planets, this magnetotail extends in a relatively simple, roughly straight configuration. On Uranus, because the magnetic field is tilted so steeply relative to the rotation axis, and because that entire tilted structure is being carried around by the planet's 17-hour rotation, the magnetotail does not simply trail behind Uranus in a straight line. It twists. Researchers studying Uranus's magnetic environment describe the resulting shape as resembling a long twisted corkscrew, spiraling behind the planet as it moves through space. An elegant, almost hypnotic consequence of geometry, born from a planet that refuses to keep its magnetic north pointed in any consistent direction relative to the incoming solar wind. There is another consequence of this bizarre geometry, one with real practical implications for understanding how charged particles interact with the planet. Because Uranus's magnetic field is tilted so steeply from its rotation axis, and because the whole system rotates once every 17 hours, the angle at which the magnetosphere meets the oncoming solar wind changes dramatically over the course of a single Uranian day. During part of each rotation, the magnetic field points in a way that leaves the magnetosphere relatively open to the solar wind, allowing charged particles to flow in and interact directly with the planet's upper atmosphere. During another part of the same rotation, the geometry shifts and the magnetosphere effectively closes, shielding the planet more effectively. Researchers sometimes describe this daily opening and closing using the analogy of a switch, flipping open and shut roughly once per Uranian day, a rhythm found nowhere else among the planets we have studied. What causes this bizarre magnetic architecture in the first place remains, like so much else about Uranus, an open and actively researched question. One compelling possibility connects directly back to the interior debate from Chapter 2. If Uranus's magnetic field is not generated deep within a small central core, the way Earth's field arises from convection in our planet's iron core, but instead arises from electrically conductive fluid motion occurring in a comparatively thin shell somewhere in the planet's outer mantle, that could naturally produce a field that is both offset from center and steeply tilted, rather than the clean, centered, axis-aligned field a deep core-generated dynamo would typically produce. Under this view, the magnetic field's strangeness is itself indirect evidence about the planet's internal structure, a clue about where, deep inside this world, the actual electrical currents generating the field are flowing. It is a remarkable thought when you sit with it. We cannot see inside Uranus. We may never send an instrument capable of directly sampling its interior. And yet the shape of its magnetic field, traced out patiently by spacecraft instruments and ground-based observations, offers us an indirect, almost forensic window into a structure we will otherwise likely never observe directly, a signature written in charged particles and twisted field lines, legible only if you know how to read it. Every major planet's moon system tends to carry the personality of whoever first cataloged it, and Uranus's moons carry a distinctly literary signature. rather than being named after figures from Greek and Roman mythology. The standard naming convention used almost everywhere else in the solar system, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. Titania and Oberon, the king and queen of the fairies from A Midsummer Night's Dream. Miranda, the innocent young woman from The Tempest. Ariel, drawn from both The Tempest and Pope's The Rape of the Lock. It is a small, elegant detail, but a telling one, a reminder that the exploration of this planet has always carried a slightly different character than its neighbors, shaped as much by literary imagination as by mythology. Uranus currently has 28 known moons, and that number has continued to grow even in very recent years. As recently as this past year, astronomers using the James Webb Space Telescope identified a new small moon orbiting Uranus, a discovery made possible only because of the extraordinary sensitivity of modern infrared instruments capable of detecting faint objects that would have been utterly invisible to Voyager's cameras during that single brief flyby in 1986. It is a quiet, ongoing reminder that even the most basic census of what orbits this planet remains incomplete, updated as recently as the last few months, with the strong likelihood that more small moons remain undiscovered even now. Among this growing family, 5 moons stand out as the major satellites, substantial enough to have been studied in real detail even during that brief Voyager flyby. Miranda, Ariel, Umbriel, Titania, and Oberon, ranging from a few hundred kilometers across to roughly 1,500 kilometers for the largest. Titania, still considerably smaller than our own moon, but substantial worlds in their own right. Miranda deserves particular attention because it may be the single strangest moon documented anywhere in the solar system. Voyager's brief pass captured images of a surface unlike anything scientists had previously seen. A jumbled, chaotic patchwork of wildly different terrain types sitting directly adjacent to one another. Smooth plains abruptly giving way to enormous fractured ridges and towering cliff faces, including one feature informally nicknamed Verona Rupees, that may be among the tallest cliffs anywhere in the solar system, dropping an estimated 5 kilometers or more, roughly 5 times the height of most cliffs found on Earth. Scientists sometimes describe Miranda's appearance as looking as though the moon had once been shattered into pieces and then haphazardly reassembled, its geological history seemingly stitched together from mismatched fragments. Exactly what process produced this fractured patchwork appearance remains debated, with leading theories involving intense tidal heating, gravitational flexing caused by Miranda's orbit around Uranus, generating enough internal warmth to partially resurface the moon in a chaotic, incomplete fashion. Beyond the sheer visual strangeness of moons like Miranda, a quieter, potentially more profound question has been building steadily in recent research: the possibility that some of Uranus's larger moons may harbor subsurface oceans, liquid water trapped beneath their icy outer crusts, warmed and kept liquid by internal heat sources and tidal flexing from Uranus's gravity, not unlike the subsurface oceans confirmed at Jupiter's moon Europa and Saturn's moon Enceladus, 2 of the most closely watched targets in the entire search for life beyond Earth. This is not yet a confirmed discovery. Rather, it is an increasingly plausible hypothesis built from modeling the internal heat budgets of moons like Titania and Oberon, and from subtle evidence in how these moon surfaces appear to have been geologically active in relatively recent history. Evidence of resurfacing that hints at heat sources still active or recently active beneath their icy shells. If confirmed, even one such ocean orbiting Uranus would instantly transform this distant cold system into a legitimate astrobiology target, a place where the fundamental ingredients many scientists consider necessary for life, liquid water, chemical energy, and long-term stability, might exist in combination, hidden beneath kilometers of ice in a place almost 19 times farther from the Sun than Earth. It is worth pausing on how remarkable that possibility is. We tend to imagine the search for life beyond Earth unfolding somewhere warm, somewhere sunlit, somewhere obviously hospitable. And yet, some of the most compelling candidates currently under serious scientific consideration are hidden oceans, sealed away from sunlight entirely, kept liquid not by a warm sun, but by internal heat and gravitational flexing, sitting quietly beneath the frozen crusts of small moons orbiting one of the coldest, least explored planets we know. Uranus's moon system, catalogued from fairy tale characters and barely glimpsed during a single hurried flyby, may turn out to hold some of the more genuinely important real estate in the entire outer solar system. Saturn's rings are, without question, the most famous ring system in the solar system, bright, broad, and visible even through a modest backyard telescope. Uranus's rings occupy an almost opposite position in the public imagination, largely because, for most of human history, nobody knew they existed at all. Their discovery, when it finally came in 1977, arrived not through direct imaging, but through an elegant piece of observational detective work called a stellar occultation. Astronomers had arranged to observe Uranus passing directly in front of a distant background star, intending to study the planet's atmosphere by watching how the star's light dimmed and changed as it passed behind Uranus's gaseous envelope. But before the star's light ever reached the planet itself, observers noticed something unexpected. The star's brightness flickered, dimming briefly several times, both before and after the main occultation by the planet. Something invisible and previously undetected was blocking the star's light in narrow bands, well before Uranus itself came into position. That something turned out to be a system of narrow, previously unknown rings, discovered essentially by accident, through the shadow they cast rather than through any direct image. We now know Uranus possesses 13 confirmed rings, considerably more modest in scale and brightness than Saturn's iconic system. Uranus's rings are narrow, in most cases just a few kilometers wide, composed largely of particles that are, remarkably, among the darkest materials known anywhere in the solar system, reflecting only a small fraction of the sunlight that strikes them. Where Saturn's rings are composed largely of relatively bright reflective water ice, Uranus's rings appear to be built from material coated in dark, carbon-rich compounds, similar in some ways to charcoal or soot, making them almost invisible in ordinary visible light images, detectable at all mainly through the same kind of occultation technique that first revealed them, or through carefully processed, long-exposure imaging. This is precisely where the James Webb Space Telescope has offered one of its most visually striking contributions to Uranus science. Operating in infrared wavelengths invisible to the human eye, JWST has captured images of Uranus's ring system rendered with a clarity and brightness never achieved before, the normally near invisible dark rings appearing instead as a crisp, glowing set of concentric circles surrounding the planet, a striking bullseye pattern that bears almost no resemblance to how the rings appear in ordinary visible light. It is a powerful demonstration of how much of the universe remains hidden, simply because it happens to be dark or faint in the specific range of light our own eyes evolved to detect, and how differently a world can appear once we choose to look at it through a different kind of light entirely. The composition and darkness of these rings raise their own quiet mystery. Why would ring material around Uranus be so consistently, extremely dark, when Saturn's rings, formed from broadly similar raw ingredients found throughout the outer solar system, are so much brighter? Leading hypotheses point toward some combination of the ring's particular composition, potentially involving carbon-rich organic compounds, and billions of years of exposure to radiation and micrometeorite impacts, gradually darkening the ring material over time, a kind of slow cosmic weathering. But a fully satisfying, detailed explanation for just how dark these rings have become remains, consistent with nearly everything else about this planet, not yet fully settled. There is something quietly moving about a ring system discovered not through a triumphant photograph, but through the subtle flickering of starlight, later rendered in glowing detail by a telescope observing in wavelengths of light invisible to human eyes. Uranus's rings spent most of history completely unknown, hidden in plain sight, waiting first for a starlight shadow to reveal their existence, and later for infrared vision to finally show us what they actually looked like. Science, at its best, sometimes advances not through a single dramatic breakthrough, but through patient, opportunistic timing, waiting for the universe to arrange itself into a useful configuration, and then being ready when it does. Right now, in the current period spanning roughly 2025 into 2026, Uranus is offering exactly this kind of rare opportunity. As Uranus continues along its slow 84-year orbit, its position relative to the background field of distant stars gradually shifts. Occasionally, this slow drift brings Uranus directly in front of a star, as seen from Earth, producing precisely the kind of stellar occultation event that first revealed the planet's rings back in 1977. These alignments are relatively rare and unevenly distributed across the decades, but the current period happens to include a notably favorable window for observing several such occultations, offering astronomers a rare chance to study Uranus's atmosphere using the same fundamental occultation technique, but now equipped with instruments immeasurably more sensitive than anything available in the 1970s. When a star's light passes through Uranus's atmosphere on its way toward Earth, it does not simply switch off cleanly, the way it would if Uranus had no atmosphere at all. Instead, the starlight dims gradually, and its color shifts subtly as it filters through progressively deeper, denser layers of Uranus's atmosphere. By capturing this dimming and color shifting with extreme precision, astronomers can effectively use the star as a natural probe, extracting detailed information about atmospheric temperature, pressure, and composition at various altitudes, information that would otherwise require an actual spacecraft descending into the atmosphere to obtain directly. This matters enormously precisely because Uranus has never had a dedicated orbiter or atmospheric probe. Everything we know about its atmospheric structure below the outermost visible cloud layers comes either from that single brief Voyager flyby or from these occasional precious occultation events observed from telescopes here on Earth or in Earth orbit. The current alignment window represents the best opportunity in years, and in some respects since the earliest era of Uranus's discovery, to gather fresh, detailed atmospheric data using instruments and detector technology that did not exist during previous favorable alignments. Early results and ongoing analysis from these recent occultation observations are, quite literally, still being processed and published even as this documentary is being written. This is one of the more unusual aspects of covering Uranus science at this particular moment. The genuine possibility that findings described here as current understanding may be meaningfully refined or even substantially revised within a matter of months as researchers continue working through the data these rare alignments have provided. It is a reminder that this is not a story being told from a place of settled historical certainty, the way we might describe the outcome of the Voyager flyby itself. This is a story still actively being written, its next chapter arriving from observatories on Earth even now, one flickering starlight measurement at a time. There is a particular kind of patience required to do this work well, the willingness to wait years, sometimes decades, for the solar system to arrange itself into a useful configuration, and then to be ready, instruments calibrated, telescope time secured, the moment that configuration arrives. Uranus, distant and slow-moving as it is, does not offer these opportunities often. The astronomers currently poring over this new occultation data are, in a very real sense, doing exactly what their predecessors did in 1977, watching a star flicker as it passes behind a planet and finding in that flicker information no direct image could ever provide. Every 10 years, the scientific community responsible for planetary exploration in the United States undertakes an enormous, rigorous exercise, a decadal survey, in which hundreds of researchers collaboratively evaluate the entire landscape of open questions across the solar system, and recommend which mission concepts deserve the highest priority for the following decade of exploration and funding. In the most recent survey covering the current decade, the single highest priority flagship mission recommended by the planetary science community was not a return to Mars, not a mission to one of Jupiter's moons, but a dedicated orbiter and atmospheric probe to Uranus. After 40 years defined by a single brief flyby, the scientific community formally, collectively agreed this is where the next major investment of national resources and scientific attention should go. The proposed mission, generally referred to as the Uranus Orbiter and Probe, would represent an entirely different category of exploration compared to Voyager's brief passage. Rather than a few hours of observation before continuing outward forever, an orbiter would settle into long-term residence around Uranus, potentially for years, conducting the kind of sustained, repeated observation that has already proven so valuable in resolving mysteries at other planets, mapping the magnetic field in genuine detail rather than through a single solar wind-compressed sample, precisely measuring the planet's gravity field to finally help settle the ice giant versus rock giant debate and observing seasonal atmospheric changes directly, rather than inferring them indirectly through distant telescope monitoring from Earth. The mission concept also includes a dedicated atmospheric probe, a smaller craft that would separate from the main orbiter and descend directly into Uranus's atmosphere, measuring composition, temperature, and pressure at increasing depths before eventually being crushed by the enormous pressures deeper in the atmosphere, providing exactly the kind of direct atmospheric sampling that occultation observations, however clever, can only approximate from a distance. But reaching Uranus is a genuinely difficult undertaking, and understanding why reveals just how remote this planet truly is. Because of the enormous distance involved, roughly 2.9 billion kilometers, or 19 times the distance between Earth and the Sun, any realistic mission requires a gravity assist from Jupiter, using that giant planet's immense gravitational pull to slingshot the spacecraft outward with far greater speed than its own propulsion could achieve alone. This dependence on a Jupiter flyby means mission planners must work within narrow, specific launch windows, periods of only a few years, occurring roughly once every decade or so, during which Jupiter happens to be positioned correctly relative to Earth and Uranus to make the gravity assist trajectory work. Miss one of these narrow windows, and the mission may need to wait years, or be redesigned entirely around a less efficient trajectory. Even under the most favorable launch window and trajectory, the cruise time to Uranus, the sheer number of years the spacecraft would spend traveling before arrival, is expected to exceed 13 years and could stretch considerably longer under some trajectory options. Consider what that actually means in human terms. A graduate student who joins the mission team as it begins detailed development might not see the spacecraft reach its destination until well into their career, possibly not until they are approaching retirement themselves. Some of the senior scientists currently advocating most passionately for this mission, the researchers who have spent entire careers building the case, publishing the papers, and pushing the proposals that led to this recommendation, will very likely not be alive, or will be too elderly to actively participate by the time any spacecraft launched today would finally arrive and begin returning its first real data. This is one of the more quietly sobering realities of deep space exploration, a form of scientific patience and generational sacrifice that has few parallels in other fields. Scientists are, in a very real sense, being asked to dedicate significant portions of their careers toward a discovery they themselves may never personally witness, trusting that future colleagues, in some cases scientists not yet born, will eventually carry the work to completion, will watch the data return, and will finally answer questions that have remained open since a single brief flyby in 1986. And so we arrive at where this story currently stands. A planet visited exactly once for a matter of hours, its magnetic field distorted by unlucky timing, its interior genuinely unknown, rock or ice we still cannot say for certain, its faint internal heat only recently confirmed to exist at all, its storms and seasons only now being tracked across the patient span of decades rather than hours, its moons hinting quietly at oceans we have not yet confirmed, its rings glowing in infrared light only because we finally thought to look that way, and its atmosphere, right now, in these very months, being probed by starlight flickering behind it as it drifts along its slow 84-year path. Uranus sits there in the dark, one properly funded, patiently built spacecraft away from potentially rewriting large sections of planetary science. The mission has been named the highest priority by the scientific community that studies these things for a living. The narrow launch windows continue to arrive and pass, roughly once a decade, waiting for the moment political will, funding, and engineering readiness finally align. Somewhere, right now, a researcher early in their career is likely working on some small piece of the puzzle that a future orbiter mission will eventually need, unaware perhaps that they may be the ones still working on this project decades from now, still waiting, the way an entire scientific field has been waiting for 40 years already, for humanity to finally go back. Step back now, far enough that Uranus shrinks to little more than a pale point of blue-green light, one dot among the 8 major planets orbiting an ordinary star, itself one among hundreds of billions of stars scattered across a single galaxy, itself one among an almost incomprehensible number of galaxies filling the observable universe. From that distance, the questions we have spent this evening sitting with, rock or ice, warm or cold, tilted by violence or by some gentler process we have not yet imagined, can feel almost impossibly small. And yet there is something worth holding on to in the smallness of it all. We have visited this world exactly once, for a matter of hours, out of the roughly 4.5 billion years it has existed. And out of that single brief glimpse, an entire generation built a confident, settled story about what kind of place it was. Bland, featureless. Understood. It took decades of patient relooking, new instruments, careful reanalysis of old data, and no small amount of humility to realize how much that first glimpse had missed. Perhaps that is the quieter lesson tucked inside this planet's story, one that reaches beyond astronomy entirely. How often do we mistake a brief encounter for a complete understanding? How often does something or someone get filed away as simple or boring or fully known, simply because we never looked again, never watched long enough for the storms to reveal themselves, never waited for the starlight to flicker in just the right way? Uranus still spins out there tonight, tipped over on its side, carrying its poles through 21-year stretches of unbroken light and unbroken dark, its moons quietly orbiting a tilted axis shaped by a collision older than most of the solar system's current geography, its rings glowing faintly in wavelengths our eyes were never built to see. Somewhere in its deep interior, matter we still cannot properly classify sites under pressures we can barely calculate, radiating a whisper of heat outward into the cold, patient dark, heat that started as violence billions of years ago and has been quietly, stubbornly leaking out ever since. We do not know yet what Uranus truly is, deep down and firsthand, not simply inferred through modeling and gravity data and shadows cast across starlight. We know only that we have asked and that a single brief visit was never going to be enough to answer. Somewhere, a spacecraft that does not yet exist is waiting to be built, waiting for a decade-appropriate launch window, waiting to begin a journey longer than most careers, carrying instruments toward a world that has been patiently keeping its secrets since before Voyager, before Herschel first noticed it through a telescope in 1781, before humans existed at all to wonder about it. Uranus will still be there when it arrives. It has nowhere else to be. It has simply been waiting quietly on its side for someone to finally come back and look again,